You can so isolated footing, actually when we talk about the footings, there are so many type of footings available in the structural engineering. So today this presentation is basically we are talking about type of the isolated column footings, the bearing capacity of the soil, the critical section, check for the development end, and the reinforcement requirement. So when you talk about these isolated footings, right? So the pad footing, slope footings, you can see here the different kind of footings being used in the building design, right? So what do you mean by the bearing capacity? So the bearing capacity in the sense that when the building is subjected to any loads, so the final point is to transfer the load from the structures to the soil is the footing. We call this is the another kind of word, that is the soil structure interaction. The soil structure interaction is the meaning of where the structure and the soil will be getting interacted each other. The bearing capacity of the soil is in the sense that the foundation you are putting on the ground will be needed to will be able to take the load that is transferred right from the buildings to the soil. So this is why I'm telling, so the foundation type, the foundation standard, whichever you use in the structures has to be done through the soil investigations report. Okay. So then the size of the footings depends on the bearing capacity of the soil. The load on unit area below the footings should less than bearing capacity soil to prevent the settlement of the footing. The gross bearing capacity, the total pressure acting at the base of the footing, including the self weight of the footing, weight of the columns, overburden pressure of the soil above the footing, etc., is called the gross bearing capacity. The net pressure at the base of the footing after deducting the weight of the excavated soil is called safe bearing capacity of soil. So these the bearing capacities let's talk about. You can here see these the safe bearing capacity on the rock is 450 to 300 kilonewtons per meter square. So if any foundations could place on the bedrocks, can you kindly mute your microphone, please? Okay, rock. Then the non-cohesive soils, gravel, coarse, sand, medium, fine. So what we always find in the industry is 100 to 450. Then cohesive soil, so it is 50 to 450. Usually in Sri Lankan cases, it is very difficult to find the bedrock within a short depth of the soil. It might go up to the 20 meter, 15 meter, etc. So then usually we will find for the isolated footings or the raft footings, the number 2 and 3, non-cohesive soil and the cohesive soil. You can see the non-cohesive soil, the gravel, coarse sand, medium sand, fine sand, etc. will have a higher safe bearing capacities comparatively the cohesive soils where the soft, hard, stiffy clay are considered. But however, these two type of the soils are being oftenly available in Sri Lankan's foundations design. And also you need to make sure one thing is that when the foundation's designed to be done, the soil investigation report we call, the soil investigation has to be done. So what do you mean by the soil investigator? So there are so many companies and institutions, they come and do the few tests and they drill and take the core sample out and check whether what is the bearing capacity, C value, cohesion, the phi value, friction angle. Depending on all these things, they will give the recommendations for the foundation type. And also it will give an insight, it will give the highlights of the bearing capacity that we can use for safe margin. So this is the critical sections. Actually, we are going to learn these things in punch-in shear and the critical shear, etc. Okay, so I will, you can see the depth, everything's what we discussed. In anyway, anyhow, I will talk this one through the example, then you will be easily understand. So we check whether these surface, now we have to do few checks. One is just outside the column sections where it is getting inside to the footings will be safer or not. So then we assume that the distance of the D, so what we can, how the shears to be transferred. So basically if the column is not, column loads are not eccentrically transferred the load, you need to work on the shear. So if there is any eccentric, so then the flexurer also will take part of that and the designs to be carried out. So this is another critical section that you need to make sure in the design calculations. Okay, so then I will leave it for basic understanding, and I hope, sorry. I hope everyone can see this calculation. Okay, so please quickly read the example. Then we will try to finalize the designs and the calculations by understanding the fundamentals. The question is a 25 millimeter square columns carried a load transmit to the foundation. Safe bearing capacity of the soil is 150 kilonewtons per meter square. The question is design a square pad footing to resist the FCU. The characteristic concrete strength is 25 megapascal, assuming that the material strength is 250. But here nowadays we use the 460. Instead of using this one, you may able to you may able to use the existing RB sections where the 500 or the 460 megapascal considered. Loading, the dead load, self weight of the slab, you can assume here the slab is 0.12, it means 120 millimeter into 1.85 in the 2.8 into 24 is the density of the concrete. So this is what going to be find it out is the effective area for the column, and we will find all the load. So it will be comes around 10.7 kilonewton, and also the weight of the beams. Once again, you can calculate it here 0.225 meters into 0.120 and into the 1.2875. Okay, so this is also multiplied by the density of the concrete, that will be coming 1.25 kilonewtons. So self weight of the beam D, you can similarly count it as 0.225 and 0.5 the depth of the beams, and the 2.88 the width, and the after that once again the 24 kilonewton. Okay, then other one is self weight of the columns above the beam, then the 0.225, then the finishes of the slab 1.2875 into 2.8 into 1 kilonewtons per meter square, that will becomes 3.71. The block wall is 0.125 into 1 into 4.5 into 20, 11.21. Total dead load is summation of above values. It will be coming around 38.9 kilonewton. So let's assume at least into the, I don't mind, you can round it off to the 40 kilonewton. Imposed load also you can similarly count it, 1.285 into 2.75 into 1.1. So the import load, finally it will becomes 4.085. So the ultimate design load 1.4 into 38.9 into 1.6 times 4.01, altogether it will be coming 61.075. The design axial load, ultimate axial load divided by 1.4, so that will be coming 42.14, because we don't design the foundations for the ultimate limit state, we only design for the serviceability limit state, so you can divide by 1.4. Okay. So then okay, total weight including the footing weight, serviceability load plus the 8% of the axial load, you can take it. So the it will be around 45.5 kilonewton, right? Then we will take the plan area. So the plan area is the footing. We assume that the bearing capacity of the soil is 150. So altogether it is required 0.3 meter square. So it will be like 600 by 600 base. You need to assume that the area will be coming 0.36. The required area is 0.30. The self weight of the footing also can be calculated 1.1. So the actual load will be 42.1 into 1.2. So the W divided by the 0.36. So that all together will be 120 kilonewtons per meter square. So their bearing capacity is lesser than the higher than the actual one. So the one check is satisfied. Other one is a design movement. Let us see the design ultimate movement. The total load is 61.1075. The earth pressure is 169.74. So this will be counted for the ultimate limit state. And the maximum design moment M, the resultant force into the length, occurs at the face of the column. So 169 into 0.6 into 0.1875 into 0.1875. It means, so it will be counted up to this surface. So altogether it will be coming 1.7912 kilonewtons meter. So then we will Okay, this is what it says. Okay, so the total weight we have been calculated. Then the plane area, self weight of the footing. So everything we calculated. I just going back, and this one also been calculated, like design movement 169. So the earth pressure will be coming 169. So we know that the depth for this one is 0.875. So this has to be multiplied by 0.875. The total load, you have to find it out, the resultant force coming here. This 61.1, sorry, 169.74 multiplied by 0.875, and it, don't worry, I will share these one with you. So the maximum design moment, you can see the 169.6 is the one side length of the footing, and 0.875 is the distance in between the edge to the surface of the column, and into the 0.875 divided by 2, that is the center of the area. So finally you will be find the 1.7912 kilonewton meter. The ultimate movement you can find it out quickly. So the D average you can assume total H minus cover minus 5. So the 5 is the bottom layer reinforcement diameter. Altogether it will be coming 90 millimeter. Ultimate design moment is 0.156 FCUD times BD squared. So that will be 18.9540, because this will be coming from the 8110 code. So the since M is greater than the MU, so the no compression reinforcement is required. So that will be satisfied. The main steel K is divided by the M over FCU or BD square. The 1.7912 into 10 to the power 6, 25 into 600 into 900, 90 by 90, so equal, that will be 0.0147. The z is equal d times 0.5 times the 0.25 times the k over zero point 0.9. So altogether the D is coming 88.5. So usually we don't allow the effective Z lever arm is going beyond 0.95 times D. That is a code requirement. So if since it is coming the 88, so we have to consider the 85.5 for the effective height. So this check always you need to do in the beams analysis as well. So the AS is calculated 88.20 millimeter squared per meter. So AS minimum you can calculate 0.24 percentage. So the AC is coming approximately uh, 216 millimeter squared. So that is the minimum requirement. AS minimum in the footing you have provided the 0.25. So then the minimum reinforcement has to be provided rather the design value. Okay. Then we will discuss about the distributions of the reinforcement. Okay. We know that the LC is equal, the total length is a 600 millimeter. So then the one face is 600 divided by 2. Center of the columns is the 300 millimeter. Then you can calculate 3C plus 9D plus. So the C is 225. C is the one the shorter width of the columns divided by 4. D is the effective depth. So that is the total 90. So then the that value will become 371.25 millimeters. So the LC should be lesser than this. Hence, provide the this is the distance. So you can provide 3h as a distribution uniformly across the full width of the footing parallel to the XY axis. Now we will see the punch in shear. We call the punch shear. So the stresses on the surface from the surface and the 1.5 times D. The P critical, the column perimeter and plus 8 times the 1.5 D, right? Or the P critical 4 times 225 plus 3D. So once you calculate this one, the pre critical is coming 1980. So whatever the largest you have taken. So the area within the perimeter is 225 plus 3D. So this will be 0.2 into the 10 to the power 6. So that will become in a huge value where the most probably 250 millimeter squared. The ultimate punch in shear is load divided by the shaded area, the 169.75, the 0.36 minus 0.245. The total area is 0.6 into 0.6. That's why here the 0.36 is coming. So after that the value is coming 19.5205. Define the punch in shear stress V. The V is equal V P critical into the D. The 19.52 into 0.5 into the 10 to the power 3 and 19 into 10 into 90. Then 0.1095 is the newtons per millimeter square, the permissible 0.8 into the square root of FCU. So that will be coming 4 megapascal. The concrete design stresses is the VC it equal to 0.79 100 days over BD into 1/3 on the 400 divided by the D over 1/4 in the gamma M is the concrete shear safety factor, right? So the finally we will come to this calculation. So the VC is equal to 0.7 times 100 into 88.2 divided by 600 into 90 into 1/3 400 divided by 90 into 1/4. So altogether it will become 1.25. The VC is 0.79 into 0.45 into 1.45 divided by 1.25. So altogether it will be coming the 0.5069. So the VC is greater than the V punch in failure will unlikely take at the 100 millimeter depth of the slab is acceptable. So if this requirement has not been satisfied, you have to increase the slab width definitely and see the requirement of the shear value. The reinforcement details 225 millimeter. So the area we have been finalized. So you can put 4H10, right? The reinforcement arrangement as followed. So this is how the main reinforcement will be located within the bottom net. I hope everyone understand this one because since you are in the site experience in the day-to-day works at the house construction, you are almost able to understand what are the fundamentals behind that. With this, the footing calculation for the building being discussed here, right? So thank you very much.